Today we're going to be talking about the kinetic molecular theory, which is an application of how gases behave when we do things with their temperature, with their pressure. So it's basically explaining why gases are the way they are. So when we look at the kinetic molecular theory, a theory is something that explains the way we observe things to be in nature. So when we look at something like a theory versus a law is more of a mathematical relationship between things. So a law can explain things with math, whereas a theory explains the way things are based on what we've observed. So the following are the 5 components of the kinetic molecular theory that explain how we observe gases to be. So the first thing is we observe that gases are particles that are in constant motion. So it could be one singular particle like an atom. It could be a combination of particles like carbon dioxide, where you have a couple different particles that are atoms attached to one another chemically. But any of those, they are in constant random motion. So the first part of the theory says that these particles never stop moving. They are always moving in some capacity or another. The second part of the theory explains that they're constantly colliding with one another. So if you think about particles sort of being like, almost like if you've ever seen bingo before, how the balls that get pulled for bingo are always bouncing around and hitting things. That's sort of what you can imagine particles being like. So they're always hitting each other, they're always hitting the walls of their containers, but based on the kinetic molecular theory, they're not losing any energy. So when they hit something, they don't slow down. They're essentially just hitting something and moving on to hit something else and hit something else and hit something else. The third part of the theory is explaining how small these particles are. And if we looked at the volume of just one singular particle compared to the volume of everything else inside of that container, it's negligible. So we essentially say that they have no volume because it would be rounded to almost zero because they are so incredibly small. We also say, as part of this theory, that gases are not attracted or repelled from one another. So they aren't drawn to attract to one another. They're not repelled by one another. They're simply just floating about, moving in constant random motion, and they occasionally just run into each other. And we also say that the kinetic energy, or how much they're moving, is proportional to how warm it is in that container, or how warm those gases are. So what that means, proportional, means that if one goes up, the other goes up. So if we see the temperature of a gas going up, we see their energy or their movement going up as well. So making things warmer makes them move faster. So the way we apply that is we look at temperature first. So temperature makes these gases speed up. If we have things that are warmer, they're going to be moving faster in terms of the particles. More heat means more collisions. More collisions means more pressure. So when things are colliding into the walls of their container, into each other, we call that pressure. So if there's not that many collisions happening because they're not moving very much, it would have a low pressure. But the more they collide, the more the pressure builds up. So if we see the temperature increasing, the pressure is also going to be increasing if we keep the volume the same. So let's say I have 100 particles in a box. If I heat up that box so it gets warmer inside, those particles are going to be moving faster and they're going to be having more collisions, either with other particles or with the walls of the container. If I don't make that container any larger, the pressure is going to increase inside of it. So that's what we see when we look at something like tires. If we add more gases to a tire, or if a tire gets warmer, the pressure inside of that tire gets higher and the tire can actually pop. So when you drive vehicles for a long amount of time and the gas inside of those tires gets really warm, it has a higher likelihood of popping because the pressure is a lot higher. We also see that if temperature decreases, the pressure is also going to decrease, because if the temperature is lower, the particles are hitting less things. That means the pressure is going to go down because they're not hitting as much stuff. And we also see that volume has a place in this as well. So if we have volume getting smaller, there's less space for those particles to move, so they're inevitably going to hit more stuff. And if we hit more things, we have a higher pressure. So smaller volume, shrinking something, means there's going to be more collisions because there's less space to move, meaning the pressure increases, meaning if the pressure goes up, the temperature goes up. So we see pressure and temperature being related to one another. But volume and pressure are what we call an inverse relationship. As volume goes down, pressure goes up. So pressure and temperature are a direct proportional relationship. Volume and pressure are an inverse relationship. So if volume goes down, pressure goes up. We see the converse, and you can almost see this in this picture here, that as the volume gets bigger, the particles are running into each other less because they have more space to move. They're not bouncing off of as many things. So the pressure is going to go down as the volume gets larger. So these are the applications of the kinetic molecular theory. So when we look at the kinetic molecular theory, we're essentially looking at three individual variables: temperature of a gas, pressure of a gas, and volume of a gas. Now, when we look at this, we're kind of looking at it in terms of their relationships with one another. The way these are more detailed described in chemistry is actually called gas laws. So when you take chemistry, either next year or the year after that, you're going to see that these relationships have a mathematical law relationship explaining how the volume and the pressure are related numerically. Right now, we're talking about it in terms of a theory, so we're looking at it more qualitatively versus quantitatively. So in the lab that you're going to be doing, you're going to be applying this information and trying to understand how temperature, pressure, and volume are all related to one another.